Now we are already a few minutes late, but I was waiting for other students to join in, but I think we might start now. Today we are starting the second part of your course. The first one, led by Dr. Walkowiak, was dedicated to Java programming, Java environments, whereas now this part of the lecture will be about the operating system, the programming environments natively available when you are programming in C, and problems how the operating system is organized. So the two blocks were combined in this course. In normal computer science or computer engineering programs, they are separate courses, but for you it is a combined course of the two. So I am leading the second part, and with you, and you will have with me the exam at the end of the term. As Dr. Walkowiak has already told you, at the end we are planning a short test where you will have to answer to questions both from my part and from Dr. Walkowiak's. What he didn't tell you, because he missed the point, that 2 years ago the program has changed and this has the status of an exam, which means that we will be doing in the during the last class the test, but you also have possibility to take the exam in the normal exam session if you would rather do that. But that would not be a test, that would be questions to be answered. Okay, so that is how we will proceed. So that we don't waste any more time, I will be starting now the lecture. During the laboratory, I will be telling you about my requirements about the laboratory and organization of that, but I don't want to waste the time for this. If you have any questions as it is, please ask now. If not, I will switch off my video and start sharing my screen. I don't hear anybody wanting to speak with me now, so I will.
I'm sorry, is there an option that you could perhaps speak a little bit more loudly? It's very quiet.
Okay, I think that the point is that I wanted to be seen in the screen, and that was the reason, and I was too far from the microphone. Is it better now?
Yes, it's better.
Okay, so I will try to speak a little nearer.
Sorry, I also have a question. Does the final test also include Dr. Walkowiak part, right?
Yes, yes, it will be combined. I don't know how many questions at the moment, but there will be mixed questions from both of them. It will be a test run in the e-portal that is in Moodle, a standard single answer test questionnaire.
Okay,
thanks. Okay, so we'll start off my part of the presentation. Today I would like to have a short introduction what is the operating system, what are the different types of the operating system, and to start off I would like to show you the standard picture, which is always shown when we are addressing problems of operating systems, then that if you consider any computer, doesn't matter whether, oh, I will switch off video because that is just making it more difficult for you to follow. Okay, when you look at this as any computer, it doesn't matter whether it's a mainframe, whether it's a laptop, or even whether it's a smartphone, you have hardware, which you see, which is at the center. You have the operating system, which which is the main layer, software layer, to be clear, to make running applications and developing applications easier. And on top of that, you have programs of applications. Some of the programs are dedicated to what you to specific tasks. Sometimes you need to buy them or install them. Some are pre-installed with the operating systems, and those pre-installed programs usually dedicated to organizing the problems of operating system of the environment. They are called system programs. So as a user, you look from the outside to this layered structure, and actually you see applications. You don't see the operating systems. You might think that you see the operating system because you see some system programs, specifically one of the nowadays one of the basic system programs running on your computer is the desktop, which you see on your screen. Okay, and all the commands, programs that you are running, they are applications. They are not the operating system. Operating system is something hidden between the hardware and the applications to make applications to allow applications to be moved between different computers. The whole problem being that if you have even a laptop with a different amount of memory, different external device installed, this makes a difference to the programs, so that the programs don't need to be developed for each environment separately. The operating system is put in the middle, and its main purpose is to hide those differences. Okay? There are a few number of different types of operating systems. In general, they are all very similar, but being directed to different purposes, they are called differently, and also they some parts might differ. Okay, we have the general purpose operating systems which address all the computers, whatever. We have real-time operating systems. Those are the operating systems specifically orchestrated in such a way that they support control applications, controlling manufacturing plants, controlling devices. In case of small devices and small operating systems, then you may speak about the embedded operating systems. They are a specific branch in the real-time operating systems. Then you have the multimedia systems, which are specifically dedicated to processing video images, still images, and also displays. And we have handheld systems, which are nowadays quite simplified versions of the general purpose operating system, specifically target to smartphones, which have a lot of limitations that are not present in general purpose computers nowadays. Okay, so if we look at the operating systems historically, actually the operating systems, okay, when the first computers were being built, nobody really have full appreciation of the need for an operating systems. So the first computers being built, they were built without any operating systems, but even those computers very quickly acquired some very simple operating systems, but we will not be talking about them, at least not on this slide. What in Poland was the first fully grown operating system was something which was called the George operating system. George operating systems were developed for Odra mainframes. Actually, it was developed by an English company which was called ICL. I don't know whether it still exists or not, but I think that even if the brand exists, that the company is already taken over. They have developed an operating system which was called George, and they allowed companies which were producing hardware compatible with the computers, they allowed them to use the George system without any licensing charges. And because of that, the Polish government at that time decided to use them for the Polish Odra, the mainframes being produced in Wrocław. Okay, so that was the first real operating system that you can hear about. Afterwards, what you need to know that at a certain point in our history, there was a Russian initiative that all the socialist countries, that is how they were called at that time, including Poland, of course, they had to use the same hardware and software. So they have, what they have done, they have stolen the schematics for the IBM mainframes, and they decided that different countries will be built in our block. We're building different types of mainframes, and all of them were running on the IBM operating system, which was called by IBM OS 360. Okay, so these are the operating systems which were mainly in 1970s, 1980s in Poland. At the end of 1980s, workstations and PCs came into being, and at that time, newer operating systems and newer also hardware started being developed. The main company, okay, I have skipped one thing. There is something which is called THE operating system. This is not really a commercial operating system. It was developed in some I think in Holland, but I'm not sure whether it was Holland or Belgium, but anyway, in one of those countries. It was developed by at university by Professor Dijkstra, who was a very well-known computer scientist, and he has undertaken to build an architecture that should be easier to maintain, easier to build, because the mainframe operating systems were very complex, and because of that, they were very difficult to maintain and very difficult to remove bugs from that. So the THE operating system was the first operating system which was built using the layered architecture, which means that the operating system was consisting of a number of distinct layers in the layers which were responsible for different functions. This turned out to be quite a difficult task, and nowadays you don't have layered operating systems because the layered structures added to the complexity really of the operating system, but it is still a very important milestone in the development of operating systems. When the workstation appeared, the first workstation were built by DEC, and DEC developed for them a specific operating system which was called VMS. This VMS operating system was very popular in the 80s until middle of 1990s. Actually, I know that a lot of banks were using them until the end of the previous century. So they are already forgotten, but they were a lot of solutions used there are still in use, and some of them are still not implemented in Linux and in other operating systems, which are now dominating. Okay, Unix came into being as an operating system for the workstations. The important thing about Unix was that it was developed by the Bell Telephone Company in US, and at that time, the antitrust regulations in United States did not allow telecom companies to sell software and to sell also hardware if it was not dedicated to telecommunication. So because of that, Unix, which they developed for themselves, they wanted to make it also public. They could not sell it, so they have allowed it to be used on a very open licensing scheme. And what is very important, they have published the full text of the operating system, the code of the operating system. They have made it public. So because of that, Unix became very quickly quite popular. It was used by different producers of the workstations, and depending on which producer of the workstation was producing them, it was branded differently. So for the Sun workstations, which were very popular at that time was the Sun OS. Also Solaris was for Sun's later distribution. HP workstations were using Unix, which they called HPUX, and also there was an attempt to use Unix on PCs, and that was branded Xenix. But the PCs at that time were very weak, and so they couldn't really support fully the Unix operating systems. But what is important, that this Xenix system, what was developed, was being developed by Microsoft prior to to MS-DOS. So at that time, the company, which was not known to anybody, was trying to make a version of Unix for PCs with not very big success, but they were successful enough that when when IBM started producing PCs, and the company which was really supposed to use them to develop the operating system for those machines failed to receive them on time, they have asked this Microsoft small company to produce MS-DOS on the basis of the experience using Xenix. So quite a curious situation. But what I wanted to tell you about is that Unix is quite an old operating system, but it was because all the source code was being available to all the educational institutions also. It was standard to teach operating systems on the basis of Unix, because it was the best documented what really is being done and how it's being done. Okay, so because of that, there were textbooks describing Unix, and there were also some attempts to make teaching easier on the basis of simplified code of the Unix operating systems. And based on that simplified code, published as an appendix to one of the operating system textbooks, Mr. Linus, student, have as his master thesis developed the Linux operating system, version 0 of the Linux operating system, because that wasn't even at that time branded as version 1 of the Linux. Okay, so that is how Linux came into being. So Linux is based on Unix code, but it's not Unix. It was written completely separately, and it was never implemented full Unix. Now it is quite a complex operating system, but the complexity is coming not from catching up with Unix, but in a completely different way that it was developing afterwards. So Linux started from Unix. A lot of applications in Linux are similar. I think I need to hide my taskbar. Sorry, I can't do that. Okay, so that was the Linux. The newest development used in Unix was the Mach operating system, which was addressing the main weaknesses of Unix, which was that it was not that the code of Unix was never multi-threaded. So they were attempting to make Unix multi-threaded version of Unix, and it was very successful attempt, but it was never adopted by the industry. And because of that, even though Mach was regarded as the next operating system after Unix, it just disappeared. Okay, so that was the workstations. At some time after the workstations, IBM first of all, other companies were trying to develop a very simple computer which could be afforded by homes, by people working from home, or people just enjoying computers at home. First, this was based on development of microchips, of microprocessors, which of course allowed smaller and cheaper hardware to be used. First, they were using the 8-bit microprocessors, and for those there were a lot of operating systems, but one was successful in the sense that it was adapted across different producers of computers, whereas all the others were specific to specific architecture, to specific computers, and this was the CP/M operating systems. It was really a standard for office use with 8-bit processors. And the company which developed them, which no longer exists, they had received from IBM the order I was telling you about to produce a 16-bit version, because IBM decided to enter the field of personal computers with the 16-bit processors, Intel 86, and they were trying to catch the market of personal computers, in which they were very successful, really. So, as I have said, CP/M, so the operating system which was planned initially for that was CP/M 16, that means 16-bit CP/M, but CP/M 16 was, I think, 2 years late. So IBM didn't want to wait with the release of the hardware, and instead developed together with Microsoft the MS-DOS, first versions of MS-DOS. This MS-DOS operating system, its most significant feature was that it was a very cut-down version of operating systems. Lots of things which were regarded as being essential in operating systems previously had to be cut out simply to be able to run the operating system reasonably. To illustrate the problem, I will tell you just two things. That the first PCs developed by Microsoft, as I have said, that they were using the 8088 microprocessor, which was a 16-bit microprocessor with an 8-bit bus, but the amount of memory operating system's memory installed there was in the smallest version 128 kilobytes, and in the maximum version, the most expensive version, it was 640 kilobytes. So it was less than 1 megabyte of memory. Okay, so in that memory, they had to find space for the operating system. They had to find space for running the applications. So that meant that the operating system had to be very simple, much simpler than even the simplest mobile operating system that we are now using. Okay. So this MS-DOS operating system stayed with us for a very long time. Of course, there were different versions of it, but all the versions really had the problem of being compatible one with the other, which meant that they had to be working in the similar principles with cutouts throughout them. And that meant that there were a proliferation of different security issues with them from the beginning. First, malware was propagating through the use of floppy disk. Then, when MS-DOS became popular, also with network connections, then they were propagating through the network, and this was the main issue. To make things better, Microsoft, together with IBM, decided to change its operating system, and the new operating system which they had proposed was called Windows New Technology. This was at the time when it was proposed. Let me think about it. It was about 1995, a year or two earlier, but I don't remember exactly. They have proposed Windows New Technology, in short, Windows NT. It was a completely different operating systems from MS-DOS. But Microsoft was very clever in that for MS-DOS operating systems, they have developed a desktop application to allow running IBM using different types of Windows and using mouse and so on, which earlier MS-DOS was not capable. MS-DOS by itself was not capable of. So MS Windows was an application running on MS-DOS, and this MS Windows first was not very popular, but starting with Windows 3, it became the standard to use it. In fact, starting from version 3, Microsoft started to sell MS-DOS together with Windows, calling it Microsoft Windows. And those versions of Windows were being run in parallel with Windows NT. Windows 95, then 98. Millennium Edition was the last version of Windows which was using MS-DOS. With that, Microsoft terminated MS-DOS completely, and instead of that, started developing Windows New Technology. And, you know, from that, branch of development. You had Windows 2000, XP, 2003, Vista, Windows 7, and now Windows 10, still Windows 10, though there are prototype versions of the next one already. Okay, so that is how it worked. What is important is that Windows NT was an operating system with complexity and capabilities similar to workstation operating systems. And because of that very quickly workstations and PCs became just the same. So nowadays, when we are speaking about workstation or a PC, we are not speaking about any differences, neither in the hardware nor in the operating system. We are mainly speaking about prices and capabilities that simpler versions of workstations are called still PCs, more complex are called office workstations. But there is no difference in the principles of working. Okay, when mobile became very popular, a new branch started. I have not spoken about iOS, that means the Apple version of workstation operating systems, but when mobiles became popular, mobile versions based on Linux. The Android system was developed based on workstation iOS, which was also initially started with some architecture based on Linux. The iOS was produced. These operating systems, even though at the roots are Unix or Linux, nowadays they are completely different. So they have also different capabilities. Okay, so to continue discussion of the historical problems, I wanted to start off telling you that initially, as I have said, computers were not being very efficiently used because there was no operating system, which means that all the software had to be developed for the very specific single computer that you wanted to run it on, which wasn't really very efficient economically and so on. What started off was what started off operating systems initially was that there were libraries, standard libraries being developed, so that different computers were using the same libraries. The libraries had to be customized to each computer separately, but the software at source code could be transferred between the computers, and that was the beginning of the operating system. The libraries, the drivers were kept by the companies, and those types of operating systems, those types of software, because they weren't called operating systems at that time, so were just some libraries which were all the time available to software that you were running on the computer. At that time, what started with that was that as I have said, we had just libraries. Okay, so that was called that you could transfer source code, but not binary code. And that was, of course, a limitation at that time. So I will be telling you how that was being overcome. And that was really being overcome by something which is called a resident monitor. But before we start with the resident monitor, which was the precursor of operating systems, I need to tell you a little bit about something which is called batch processing. Batch processing was an idea how to use computers more efficiently at the time when the computers were just works of art, really, because each one was completely different, maybe not completely, but significantly different from any other. At the beginning of computer manufacturing, the companies manufacturing computers were not building computers on the shelf. Instead, they were taking in advance orders from different computer users for a specific configuration of a computer. So each computer, even though each one was called IBM 360, actually each one was a bit different, had different amounts of memory, different input-output device controllers, hardware controllers. So there was a lot of difference in what external devices they had also, and so on. So the software had to be customized. But that was not the only thing. Also, a lot of the software had to be developed in-house. And for that, you needed to work on the computer directly. So you had to start the computer from scratch, load a lot of software for it to become intelligent, and then start doing your work. This was taking time, and very often it was very inefficient, because if there was any error in the input data, you had to stop, go and print new version of the input data. The main input devices at that time were punched tapes, which means the paper tapes which punched holes in them, and you had to repunch the whole tape and start on again, and the computer was idle at that time. So to improve the efficiency of the use of the computer, the administrative management teams decided to move the programmers, move the users out of the computing centers. Instead, the computer programmer or computer user had to prepare the data, punch the tapes, bring them to the computing center, and the computer center had to run them. Of course, not immediately, not at once, but when they wanted to, when the queue came to the specific tasks. Okay, so because of that, the programmers especially were very, at that time, had a very difficult time, because if you made any mistake, you had to prepare the new version once you got the, from the batch processing, from the computing center, feedback that you have made errors. So what was happening at that time was that different programs were being combined one with the other to speed up running. And that is why it was called batch processing. Batch means just that there is a stack of different programs stacked one after the other. and input to the computer all at once, and the computer sequentially was interpreting the input data as programs, compiling them, running them, printing out errors. Sometimes it was taking quite a lot of time. Sometimes it was just a few first punched cards or a few or a small distance of the input tape was read and thrown out because there were errors. Just the error messages were being printed, and that was all. Okay, so that was how batch processing was organized. And quite a curious thing, at that time, punched tapes were replaced with punched cards, not because they were better in any way, but it was easier to stack them into a batch, because you just had a shelf on which you were placing one after the other, the cards, and no problem with that. Okay, but there was one problem. The problem was that when you input that to the computer, it was reading the cards one by one and assuming that the last end in your program was ending your program. If a programmer made a mistake and forgot to make an end to balance the begins and the ends inside his program, one program was consuming cards from a second program, third program, and so on. So to prevent that, between the cards of the different programs, there were placed specific delimiting cards. This is the end of program 1, this is the end of program 2, and so on. But something had to understand those cards and process them. And to do that, a special program was developed, which was called the resident monitor. The resident monitor it was always resident in the computer, and it was overseeing the processing of the batch. Okay, it understood the control commands which you entered between the different parts of the batch when your program starts, when your data, where your data starts, where the second program starts, and so on. And since those cards were treated specially, not by the program, by the compilers or the running programs, but by the monitor, you prevented one set of data being overrun with another. So to achieve that, you needed a program which was active all the time, the resident monitor, and that was the beginning of the modern operating systems. Okay, the next development in batch processing was something which was called multiprogramming. Multiprogramming requires that a number of programs are run in parallel by the same mainframe. Okay, so what was the purpose? Why did someone, not me, but when was it that multiprogramming was introduced? Okay, the whole idea is that the architecture of the computers, the hardware, is such that it is very easy to perform input-output operations and processing of the program at the same time, because the input-output processing is being done by input-output devices and by small software in the computer which just interfaces with the devices. but the devices are much slower than the processor, because they are mechanical. A lot of them used, at least at that time, to be mechanical. Punch tape readers, card readers, printers, tape readers and writers, then drum readers, drum memories. They were all a lot slower than the full electronic processors. So because of that, when you run the two in parallel, it turned out that the processor was used in an insignificant percentage of the total time of processing. Most of the time, the programs were waiting for the input-output. And at that time, the processor could do something else. But what else? To achieve that something else, multiprogramming was introduced. That means a number of different programs to be processed were read from the batch file for batch processing, because as I have said, it was introduced when batch processing was the standard. And then if the processor was waiting in one program for input-output, the operating system, because this required operating system, could switch to a different program and start running it until it started input-output, and then it had to switch to a third one, and so on. So in those cases, switching between the programs was done at the moment, at very specific moments in the program, at the moments when the program was initializing input-output, because then when it initialized input-output, it had to suspend, the specific program had to be suspending, waiting for the input-output to complete. And at that time, the processor started processing a different program. So this type of multiprogramming is called non-preemptive multiprogramming, since the organization of switching between the programs is called scheduling, it was called non-preemptive scheduling. A different approach is possible, the approach in which you switch between the programs which are being developed, for example, after a fixed period of time. This type of approach is called preemptive scheduling or preemptive multiprogramming, and it needs a timer which triggers switching. Of course, even with preemptive scheduling, if you come to a point where one process has to be suspended, you don't wait for the timer to trigger switching, you switch immediately. So non-preemptive scheduling was used in batch processing because there was no advantage to using preemptive scheduling when you were just using batch processing. Nobody is waiting at that for the results, and the fewer switches between tasks, between the processes, programs which are being developed, then the fewer, the less time wasted on switching between the tasks. So, but when multiprogramming became popular, the efficiency of using the processor became very high. And at that time, it was decided that the most difficult problem is not with using the processor, but with switching between, but with especially software development, because batch processing using multitasking, multiprocessing was very inefficient for developing programs. The standards for writing code at that time were about 20 lines of code per day, because the time needed for debugging was so high that the programmers were not being used efficiently. So a lot of people were demanding direct access to the processor, as it used to be before batch processing, but of course it was too expensive. So instead of that, what the management came up with was something which was called multitasking. By multitasking, we mean a computer which shares the processor between a number of different terminals. So the users at this time were no longer required to bring the tasks to the center for batch processing. They could initiate the tasks themselves using terminals, but a number of different terminals were being connected to the same computer, which means that if one task became consumed a lot of processing time, all the other tasks, all the other terminals became dead because they could not access the processor. And at that time, time sharing or preemptive scheduling had to be introduced. So that means that the tasks had to be, each task, when it received the processor, it was receiving it for a time slot or time slice, it was called. In Polish, it was, the translation is very illogical because it's called kwant czasu, which is completely misleading because time slice doesn't need to be the same for each process. You don't need to consume it completely, because if your program suspends in the middle of a time slice, immediately the tasks are switched to another one. But when the time slice ends for one task, it is preempted. That means it's stopped and the processor is moved to a different slice. That is the need for that was to limit the response time. That means the time which elapses between you enter something on the terminal and the computer responses with some message from itself, like echoing your command line or something different. So this type of systems which use multitasking, which use time slicing or preemptive scheduling, they are called multi-access systems. And nowadays, almost all operating systems are multi-access systems. The only operating systems which might not use time sharing are a few of the real-time operating systems, because in that case the requirements are different. but all the general purpose operating systems, all the mobile operating systems, all the all the video operating systems, they are using time sharing. Okay, in case of time sharing, if you it improves efficiency a lot if you have a distinction between the foreground and background processes or tasks. Foreground tasks are the tasks for which someone is waiting for them to end. So if you are sitting on a terminal waiting for the results of your processing, this task is a foreground task. If you initiate processing and go away from the computer, such a task does not need to complete so quickly, and such processes are called background processes, and a lot of operating systems allows you to distinguish processes, that means to run them either as foreground or as background. And when you are programming, you can also have an influence whether the programs are running in the foreground or in the background. The background processes, since they don't try to, since they don't have a lot of input-output, they are very good at consuming processor time when the foreground processes are all hung on input-output, which takes a lot, which is very often because when you communicate with the program inputting something from the keyboard, you are not processing anything, okay? So background processes are used in, especially in mainframes or in servers nowadays, you would call them, to improve high processor utilization. Okay, I think I don't need to tell you a lot about this slide. Okay, there are a very specific kind of multitasking operating systems, or operating systems for multiprocessor systems. In case of multiprocessor systems, you have a lot of different organizations possible. The most popular nowadays is something which is called tightly coupled systems. That means, your laptop is really an example of that. You have a processor with a number of actually, even if it is a single processor, in fact, it is a number of processors on the same chip. Yeah. So such an organization means that you have multiprocessor chips, you have multiple chips on the on a same board and things like that. You get tightly coupled systems. They all use the same bus. They share memory. They can have more than one computer being processed at the same time. Unlike multitasking, where you had to switch between one and the other to make it appear as if a lot of tasks were being run in parallel. In case of tightly coupled parallel system, you actually, in fact, run a lot of them in parallel. Okay. So this type of architecture is very popular, especially because of the multi-core processors, which means a number of processors on the same chip, on the same die. Okay. Another type of multiprocessor systems are systems which are called clustered systems. That means a number of different computers running as a server usually. So the most popular architecture for clustered systems nowadays are blade servers, which are really computers connected between themselves using very fast networking. So unlike tightly coupled systems, in case of clustered systems, you have multiple computers with local memories, with some memory which might be shared, and with multiple buses, because each computer has its, in the cluster has its own machine bus, and connected using very fast networks. Very fast because you don't need a lot of wiring for that, and you can run it, the network much quicker than in distributed systems. And the third type of multiprocessor systems, each of them has specific different types of operating systems. In case of distributed systems, you just have multiple computers connected by network, but with software which allows remote processing from one to the other and sharing some resources. Okay. So since I have still some time, okay. So the next thing that I wanted to tell you about is that operating systems are, for a long time, they were regarded as the most complex types of software. Nowadays, one can discuss because there are some other software systems which are just as complex, but still operating systems are very complex, which means that they almost never are developed by a single programmer. So there are all the problems of repeating the same task in different parts of the software, which you know from software development in general. The same problems are in operating systems, and to limit them, there is a traditional way to approach this, that is dividing the operating system into a few subsystems. That means one subsystem is, of course, using other subsystems for performing its tasks. This is not a layered structure because the different subsystems can call one the other and the other the same one back. So it's not layered, but it simplifies management of operating system. So there are traditionally distinguished 5 parts of the operating system. That is the input-output subsystem, process management, that means running applications and programs, memory management, protection and security, I will be speaking about that in a moment, and file system. Of course, this division is independent of division between the hardware, the operating system, and application layer, because some hardware is dedicated to support file system, some software forms the main functions for dealing with files, and there are also programs, system programs, which are specifically oriented to organize files, manipulate files. Okay, the same. Okay, so file system is the part of the operating system responsible for organizing the data on disks. So that the user sees files and directories and not disks with the tracks, with the sectors and so on. Okay. Actually, in a lot of operating system, the file system is the largest part in the amount of code needed to support it. But yes. Next subsystem, which is very important, is the input-output subsystem. I have told you that one of the main problems with which operating systems need to address is how to separate the architecture of a specific computer from the software point of view. So the idea here is to use a part of the operating system, which is called the input-output subsystem. The input-output subsystem defines the drive interface. That means it defines the functions which are used actually only by the other parts of the operating system. They are never made available to the application, and those functions are specific for specific hardware. So if you have a Hewlett-Packard LaserJet, you have to have a driver. A driver is a piece of software which from one side is standard for the operating system that you are using. That means it has exactly the same functions, named the same, accessed with the same arguments as any other driver for this operating system. But the software is dedicated to the specific type of device. So for Hewlett-Packard, like LaserJet, there would be one driver. A completely different driver will be for some other, like Konica printer or something like that. Okay, so the input-output subsystem from the point of view of the operating system is a set of drivers which you need to install and the exact interface so that without any changes, the rest of the system could address in the same way the different hardware available to your computer. Okay. Another part is the process management. If you have a single process computer, which means that only one program can run on it at the same time, then process management is very simple. You just need two things solved: how to load a program so that it's running, and how to end a program. Because there is a very important thing that you probably have noticed when you were, oh no, you don't know a lot about computer hardware, so you will not know a lot also about this. But there is one thing, there is no machine instruction which tells the computer that a program ends, because a program software is being processed by the processor all the time. There is no stop. When you switch on the computer, the processor starts fetching instructions one after the other and running them. So you can't stop them. If you stop them, you just switch off the computer. Because so when one program ends, actually the operating systems must know that the program has exited. So there is a function in all the operating systems. There is a function which is called exit, which you run at the end of the program. This function doesn't stop the computer. It just tells the operating system that this program is finished and it should no longer be scheduled. It should no longer be run, and another program maybe should be loaded into the memory or just run if it's in the memory. So this part of the operating system can be very simple, because it might be just the loader or loading programs and the exit function, but it might be a lot more complicated when you have multiprocessing, when you have also multiple processors. It gets even more complicated. Okay, so this part of the operating system solves it. Okay, then we have the memory management. Again, if you have a computer which can run at the same time just a single program, then memory management just needs to prevent the program to destroy the operating system, and this operating system shouldn't destroy the memory of the program. So it is just division of the memory between the operating system and the single program. But if you have a lot of programs, then you have then you have a lot more to do, because each program has its exclusive part of the memory, which you have to make sure that one program doesn't modify another program, and also you can run out of memory available. You might have more programs running than there is memory available, and then you have to organize swapping between disks and memory of different programs. We'll be talking about that in detail. So for now, it's just this. Okay, and we are now left only with the last part, the protection and security. This is something which has to be implemented in all the subsystems, really. So in all the operating system, specific software here in the kernel or in the application level for protection and security is very small, but actually the file system must implement the requirements of the protection and security. The process management must implement the required. Memory management must implement. So it is a part of the operating system which is specifically very small, but it's distributed to all the rest. And the documentation must be very precise because of that. Okay, so looking at the system, we say that what is the operating system? The operating system is everything covering the hardware to achieve specific properties, but also there are some parts which are applications. So the operating systems consists of kernel, that is the part of the operating system which is resident inside the memory all the time, and applications or system programs which are running at specific times. Okay. So when you are running the to prevent any malware and things, you need to have proper security mechanisms, and of course you implement them in the software, but that means that some software may do everything, and some software must be limited. To that end, the CPU processor needs to support different operating mode. One operating mode is the unrestricted mode. This is the mode which is exclusive for the operating system. The operating system is often called supervisor, and for that reason, the unrestricted mode is often called kernel mode, master mode, or supervisor mode. Okay, in this mode, all the processor instructions can be executed, and processor may do any input-output operations. Processor may access and change all memory areas and all registers. So the kernel functions of the operating systems are usually run in this unrestricted mode. If you have very complex operating systems, some of the kernel functions might be run in restricted mode, in some restricted modes, but not as restrictive as for user. But in the simplest model, we just have two modes, one unrestricted and one restricted. So all the normal library functions, not kernel functions, but normal functions are run in restricted mode, and all the programs are run in restricted mode. As I have said, sometimes we have multiple levels of restriction, and in that case, some functions of the kernel are also run in restrictive mode, but not in as restrictive as the user programs. What is important is that the processor can be switched to restricted mode from unrestricted mode quite easily, but it's not so easy to switch from restricted mode to unrestricted. So how can a user program switch to unrestricted mode to do input-output or to do something else? It must call something which is called a system call. A system call is just a kernel function. So from your program, you call a system call, which is a subprogram, subroutine of your program. Actually, when you look from the programmer's point of view, it looks exactly like any other library function. But what it does is it's not running a function from the code from the library, but it's running code from the kernel. And to run it, it first has to switch to unrestricted mode. Okay. When execution returns from a system call, of course, it switches back to the restricted mode, and your program can't do a lot of things. When you are running in Windows or in Linux and you write a program, a normal program, you will see that some instructions will not be available. Some instructions will operate restricted. You will not have access to all of the memory, and you will not have access to input-output devices at all. So to achieve that, you need to use system calls. Okay. So when we speak about system calls, there are a lot of different ways how to achieve switching in the system calls. One is that there is a special process of instruction from IBM hardware architectures. It was that machine instruction was called trap. If you look at Intel machine code, you won't find any instruction which is called trap, but still those instructions capable of switching to unrestricted mode, they are called traps. So in case of Intel machine instructions, the instruction INT, that means program interrupt, that's why it's called INT, they are special instructions used to call. Okay, another approach is to use normal procedure calls. Traps were used commonly in MS-DOS, in Windows. In Unix, we used normal procedure calls, which were hidden system calls. So in this case, what was happening was really that the code for the system call was in protected memory, and when you were jumping to that memory, it caused the protection system, which was protecting memory, to cause an interrupt, and then the operating system was finding that what you were doing was jumping to a system call and executing the system function. For this to work, the addresses had to be dynamically linked. You could not jump to a code to a specific address, because you didn't know where each address was placed. So this type of approach was used in Unix, initially also in Linux, but it was turned out that in Linux you cannot do that because, okay, you can do it, but it's not very efficient. So starting from Linux version, I think version 2 of Linux is also using int instructions to jump and to maintain compatibility with Unix. It's using a special library of call stubs, a library which has the names of system functions, and inside JAS uses interrupts. Okay, sorry, I have exceeded my time of presentation. I need to end now because in a few minutes we will be starting the laboratory. So I think I have not many. I have still a few slides that I will have to present next week. So please remember where I have ended so that next week we'll continue from this place. Okay, for now it's all. I will stop sharing. If you have any questions, please ask them now.
So I have a question. Could you send the materials for the preparation for Friday group a bit earlier? Because like the Thursday evening, I think it's a bit too late for preparation. And the second,
sorry,
excuse me, can you hear me?
I hear you very weakly. Something is interrupting.
Maybe now it's better.
Voice. Yes, it is better.
Okay, so I have a question. Could you send the material for the Friday group a bit earlier, because the Thursday evening is too late for us to prepare?
Okay, I will try doing it, but the whole problem is that the Friday group at the moment is very unsynchronized from...
Yes, that's why I'm asking, because we don't have lecture and we don't have any materials for it.
Yes. Yes, I will try sending them as early as possible, yes. Okay.
And the second question, because I think, sir, you haven't checked my corrected solution on the previous laboratories, and could you check this?
We'll discuss that during the laboratory.
Okay. So at
that
Thursday,
time I will be
Friday.
Yes, I can check everything, but I think that the assignment system does not allow me to do that. So if that happened, I will know it. Okay. So, but we'll discuss it on Friday. Thank you. Okay, any other questions or comments? No, I don't hear anybody. So thank you very much. We'll be seeing, I will be seeing you in a few minutes in one of the labs. So thank you very much. Bye-bye.
Thank you, sir. Bye.